Hello, this video is about the Nobel Prize in Physics from 1915 for William H. Bragg and William L. Bragg for the services in the analysis of crystal structure by means of X-rays, an important step in the development of X-ray crystallography. You see what they generally did. They sent X-rays to a crystal, and when the X-ray reaches the crystal of course reacts, as you can see, and the wavelength and the distance between the atoms of the crystal influence, of course, the reflection pattern. And in this case, you can see that you have constructive interference, so the two signals amplify each other, and here you have destructive interference, so they cancel each other out. Okay, first from William Bragg work coming from the official Nobel Prize site. Max von Laue's discovery that diffraction patterns occur when X-ray pass through crystals inspired William and Lawrence Bragg to conduct their own studies in the area. Their contributions included establishing the relationship between the wavelength of the X-ray, its angle of incidence, and its distance between the atomic layer inside the crystal. We saw that in the pictures just before. This provided a powerful tool for studying crystal structures. Using the diffraction pattern method, it now also became possible to calculate the positions of atoms in the crystalline structure. That was, of course, a great step forward. Then some biographical information about William Bragg. His research interest embraced a few great topics. The work of Bragg and his son Lawrence in 1913 and 14 founded a new branch of science of the greatest importance and significance, the analysis of crystal structure by means of X-rays. If the fundamental discovery of the wave aspect of X-rays as evidenced by the diffraction of crystal was due to von Laue and his collaborators, it's equally true that the use of X-rays as an instrument for the systematic revelation of the way in which crystals are built was entirely due to the Braggs. This was recognized by the award of the Nobel Prize jointly to the father and son in 1915. During the First World War, Bragg was put in charge of research of the detection and measurement of underwater sounds in connection with the location of submarines. This is a summary, of course, made by me. If you want to read the complete information, you have to follow this link to the official Nobel Prize site. Then about Lawrence Bragg's work. Max von Laue's discovery that diffraction patterns occur when X-ray pass through crystal inspired William and Lawrence Bragg to conduct their own studies in the area. Their contributions included establishing the relationship between the wavelength of the X-ray, its angle of incidence, and the distance between the atomic layers inside the crystal. This provided a powerful tool for studying crystal structures. Using the diffraction pattern method, it now also became possible to calculate the positions of atoms in the crystalline structure. As you can see, this was identical to what we have just seen with his father Lawrence Bragg work. Also, this is coming on the official site. Then some biographical information about Lawrence Bragg. In 1912, he commenced his examination of von Laue's phenomenon and published his first paper on the subject. From 1912 to 1913, he had been working with his father, and the results of their work was published in an abridged form in X-rays and crystal structure from 1915. It was this work which earned them jointly the Nobel Prize for Physics in 1915. Together with his father, he has published various scientific papers on crystal structures. The crystalline state, 1934, electricity, 1936, and atomic structure of minerals, 1937. So Lawrence's chief interest at the present time are the application of X-ray analysis to the structure of protein molecules. This collaboration has succeeded in determining for the first time the structure of highly complex molecules of living matter. This is a summary by me. Coming from the official site is the complete information, so if you want to read that, follow the link. You see the used apparatus. Here you have a Roentgen source sending the rays through a slit, so you get a narrow beam that falls onto the crystal, and then you get a diffraction pattern, of course. You see the instrument in reality. Then we go to the speed read. Crystal patterns made plain and simple. When Max van Laue showed that X-rays are diffracted in crystals and form characteristic patterns on photoelectric film, he proved in a single experiment that X-rays are wave-like in nature and that crystals have a lattice-like structure. What wasn't clear was whether the structure of the crystals and the wavelength of X-ray had any influence on the diffraction pattern. The connection with its enormous practical implication was established by father and son partnership of William Henry Bragg and William Lawrence Bragg, for which were awarded the Nobel Prize of Physics in 1915. The key to Bragg's breakthrough is the fact that crystals are made of regular repeating patterns of atoms, like oranges packed in a box. Rather considering the dreadful complexity of each individual atom's contribution to the X-ray diffraction pattern, the Bragg's hypothesis was that one could mathematically predict the diffraction pattern from reflections from each successive plane of atoms within the crystal. William Lawrence Bragg proposed a simple but powerful equation showing the connection between the wavelength of the X-rays, the distance between the planes, and the angle at which the X-rays are reflected. We will see that equation later. At the same time, William Henry Bragg designed the X-ray spectrometer, a device that could examine the reflections of X-rays from crystals. Together, the two scientists used the spectrometer to analyze the structure of several salts and small molecules, establishing fundamental mathematical relationships between the X-ray diffraction pattern and the dimensional arrangement of atoms in a crystal that produced the pattern. The finding created the new science of X-ray crystallography, making it possible to determine molecular structures from the crystal form of a compound. Again, this is summarized by me. The complete text can be found here, and it was written by Joachim Nietzsche. Then we go to and this is the final part of this video, the art ceremony speech by Professor G. Grandvist. Van Laue epoch-making discovery of the diffraction of the X-rays in crystals on the one hand established wave motion as the essential quality of those rays, and on the other afforded the experimental proof of the existence of molecular gratings in the crystals. The problem, however, of calculating the crystal structures from Van Laue's formulae was an exceedingly complicated one, in as much as not only the space lattices but also the wavelengths and intensity distribution over the various wavelengths in the spectra of the X-rays were unknown quantities. It was consequently a discovery of epoch-making significance that when W.L. Bragg found out that the phenomenon could be treated mathematically as a reflection by the successive parallel planes that may be placed so as to pass through the lattice points, and that in this way the ratio between the wavelengths and the distances of the said planes from each other can be calculated by a simple formula from the angle of reflection. It was only by means of the simplification of the mathematical method that it became possible to attack the problem of the crystal structures, but to attain the end in view was further necessary that the photographic method employed by Van Laue should be replaced by an experimental one based on the reflection principle, which admitted of a definite, even though at first unknown, wavelength being made use of. The instrument requisite for the said purpose, the so-called X-ray spectrometer, was constructed by Professor W.H. Bragg, W.L.'s father, and it has been with the aid of that instrument that father and son have carried out, in part conjointly, in part each of his own account, a series of extremely important investigations respecting the structure of crystals. If a number of cubes are laid on and beside each other in such a way that one cube faces coincidences in every case with the face of the adjoining cube, whereas consequently 8 verticals which meet in one point, those angular points give a visual picture of the lattice point in the so-called simple cubic lattice. If again a lattice point is placed so as to coincide with the center point of each cube, the so-called face-centered cubic lattice is obtained, whereas the center cubic lattice has one lattice point in every cube center. With the exception of these three cases, there is no cubic lattice that fulfills the condition that parallel planes placed in any direction, whatever so as to pass through all the lattice points, shall also be at a constant distance from each other. Space lattices in the regular or cubic system must therefore coincide with one of those three or constitute combinations of them. In such lattice combinations, on the one hand, in which the condition just mentioned is not fulfilled, but consequently parallel planes placed to pass through all the lattice points in certain direction are not equidistant. That circumstance is revealed by an abnormal intensity distribution among the spectra of different orders. when the reflection takes place by those planes. From crystallographical data, it is always known how the face of a cube is situated in any given regular crystal, and there is consequently no difficulty in finding the crystal on the spectrometer table in such a way that the reflection shall take place by the planes with any prescribed orientation. The rays falling on the crystal were produced by X-ray tubes, platinum being at first used for the anticathode. The characteristic X-ray radiation of the metal consists, as is well known, of a few strong lines of narrow bands, and the very first experiments with the spectrometer revealed that X radiation that is characteristic of platinum. However, in the research undertaking to find out the nature of complicated space lattices in such an abnormal density distribution among the spectra of varying orders could constitute one of the most important of the results observed. It soon proved desirable to have available an X-ray radiation of approximately half the wavelength of the strongest platinum line. For theoretical considerations, W. H. Bragg regarded it as probable that a metal whose atomic weight was somewhere near the figure of 100 would give a characteristic radiation of the desired wavelength. Accordingly, antidotes of palladium and rhodium were produced, which fully answered the purpose in view, so that the spectra even of the fifth order could be obtained and measured. In order to take practical advantage, however, of those results, it was essential to have a method for calculating the intensity in the case of a complicated space lattice that would prove simpler than one given by von Laue's theory, and W. L. Bragg developed one. The above is a brief sketch of the method discovered by the two Braggs for investigating crystal structures. The results of the investigations appraise a large number of crystals belonging to the various systems and can only be cursorily summarized in this place. To begin with, the two investigations applied themselves to the simplest type of the regular system, represented by the alkaline haloids. It then proved that potassium bromide and potassium iodide showed the spectra that are characteristic of a face-centered cubic lattice, while the spectra of potassium chloride represented a simple cubic lattice, sodium chloride occupying an intermediate position. As it must be assumed on the strength of the analogy of these salts, both in a chemical and a crystallographical sense, they are possessed of corresponding space lattice, which would also be corroborated in another way. It was proved by those researchers that the lattice of the crystals in question consists of two face-centered cubic lattices corresponding to the two atoms, which interpenetrate in such a way that they together constitute one single cubic lattice. From this investigation, it follows that the metal atom in the crystal of the alkaloid is situated at one and the same distance from the 6 haloid atoms nearer to it, and vice versa. A relationship that was found to prevail mutus mutatis in all the crystals examined. That means the exceedingly important discovery, both for molecular physics and chemistry, that the crystals consist of atomic lattice and not, as has been always imagined, of molecular ones. Two face-centered cubic lattices can also interpenetrate in such a way that every point belonging to the one lattice is at the center of gravity of a tetrahedron whose vertices are pointing belonging to another lattice. That structure was found by the two Braggs in the diamond and afforded an experimental support for the tetrahedral arrangement that chemists postulate for the 4-coordinate carbon. On the other hand, the explanation became evident of why crystallographers have not been able to agree regarding the class in the regular system to which the diamond should be referred. It would carry us too far and be quite too complicated a proceeding to give an account here of the further investigations into the space lattices of the crystals. It will suffice to add that in the course of these investigations, the two Bragg have also discovered important relations between the amplitude and the phase differences of the diffracted rays on the one hand, and the atomic weights on the other hand, and have also shown experimentally the influence of heat on space lattice. Finally, it may be mentioned that the two investigators have also determined the wavelengths of the X-rays and distances between the successive planes placed to pass through the lattice point, with such exactitude that the error, if any, is probably at the most a few units per cent, and it is more due to the general physical constant entering into the calculations than to the measurements themselves. Thanks to the method that the Braggs, father and son, have devised for investigating crystal structures, an entirely new world has been opened and has already in part been explored with marvelous exactitude. The significance of this method and of the result attained by their means cannot as yet be gauged in its entirety, however imposing its dimensions already appear to be. In consideration of the great importance that these methods possess for research in the realm of physics, the Swedish Royal Academy of Science decided that the Nobel Prize in Physics should be divided between Professor W. H. Bragg and his son W. L. Bragg, in recognition of the service in promoting the investigation of crystal surface by means of X-rays. As you can see, this is coming from the official Nobel site. There's even more information. It's called Perspective to Parent Trap. And if you want to, I've not included it here, but if you want to read it or you want to read the original ceremony speech, you can follow those links. Here you see, by the way, what's going on. Here you have the crystal letters with the planes of atoms, as you can see. Here is the X-ray bundle coming, and you can see it is reflected, and of course it's also reflected on a deeper plane. And you can see, of course, there's a difference in distance that has to be done. That is this part, and this is the angle phi. It's also this angle. This is d, so you can calculate this part that is equal to d times the sinus of phi, and twice this part and this part. So the distance in wave the difference in distance is equal to 2 times d times the sinus of phi, as is said here, as you can see. And this is if the two rays have constructive interference, that distance is equal to one wavelength or two wavelengths or three wavelengths, as you can see here. N is an integer and lambda is the wavelength. Dus the whole number of wavelengths is equal to the distance difference, and that is equal to 2d times sinus phi. That is the equation what we saw was mentioned earlier, but not given yet. Here you see a variation of the same picture, as you can see. Yeah, okay. Next time we will deal with the Nobel Prize lectures given by the two, and we'll go further into the theory. For now, thank you for watching.